My name is Eliot Moss. I'm a retired professor of computer science at the University of Massachusetts, but still active in my research. And I've been invited to give this presentation on our project related to adding simple transactions to WebAssembly. And I thank everyone for dealing with the fact that I can't be there physically. I'm winding up a visit in Australia. So for me, it's Wednesday morning. Um, Anyway, my co-authors in this work are Professors Tony Hosking and Steve Blackburn, both of the Australian National University, and graduate students Hao Shi and Angela Upreti. So what are we about? Ultimately, we are researching and trying to build persistence for managed languages using non-volatile memory. That might include byte addressable non-volatile memory, but we'd like a setup that could work with other ways of obtaining persistence. We're interested in persistence by reachability, as opposed to the models you might see with the C language, where you specifically designate which objects will be persistent. And to make this work sensibly, with respect to multiple users, perhaps, but certainly with respect to crashes, we want our system to have ACID-style transactions in the sense you might have heard about in a database course. So supporting multiple threads, portable across a range of target systems, fairly easy to target, and source language neutral. Now, this is a research project, but we hope it could move to production. And our goal is to enable exploration of both transactional and persistent programming languages. And we want our design to admit relatively efficient implementation, including a variety of optimizations. Now, we had been using some other targets in earlier times, but a bit over a year ago, we looked at WebAssembly and said this would be a great target for us. The persistence by reachability approach meshes well with the GC extension to WebAssembly, but you also have the linear memory there, and that can be made transactional as well. We can interoperate with, but we would not absolutely require WebAssembly threads. So we've decided to put out at least an initial offering of simple transactions. And by that, we mean avoiding fancier things like nested transactions. Now, persistence will build on the simple transactions extension, but I'll mostly be talking about transactions in this talk and not as much about persistence. So some of the benefits of using WebAssembly for this work is we can tie in with existing WebAssembly engines that have mature design and an active community. It's a comparatively modest extension semantically for what it does. The design and the prototype we can make available to an active, broader community. We believe this fits with WebAssembly and its overall ethos of taking hardware and OS type resources and making them available in a machine and OS independent way, and language independent coming down from the top, if you will. So a goal here with the persistence is to present non-volatile memory hardware with a clean, easy to use semantics. So our approach to simple transactions. So we create transactional versions of the stateful parts of WebAssembly. Now, an obvious thing to think about would be the GC objects for the persistence and transactional objects by reachability. So we add T structs and T arrays to the existing structs and arrays. We add transactional global variables, T global, transactional linear memory. So these exist as things alongside, not replacements for the existing stateful parts. The idea here is that a single engine could support both transactional and non-transactional work or programs. Now, this definitely implies additional types, particularly when you're talking about the structs and arrays. We decided to add a kind of parallel collection of opcodes to make it clearer when you're doing a transactional operation versus an ordinary one. And that's mostly done by adding a prefix to the opcodes and likewise to the types. However, with the opcodes, we could mostly avoid that if you were willing to say, okay, in a transactional scope, this opcode means this, and in non-transactional code, it means this other slightly different thing. Now, using distinct types helps avoid potentially costly dynamic checks of, do I have a regular array or a transactional array? The clear separation of transactional and non-transactional data avoids all kinds of messes you can get into if you're allowed to use both sorts of data at the same time. So it can be a semantic mess and an implementation mess. For example, you get down in the middle of executing a transaction. For some reason, it's going to fail, perhaps by a conflict with another transaction. So the transactional things will wind back. But what about the non-transactional ones? What happens to them? And so forth. So while our hope is that an engine, in our spec, an engine would support both, but you probably would not mix them all that much in a single program. All right, so let's get on to the semantics of these things. So ACID, but in the case of the transactions extension alone, not the durability. Persistence would add the durability. We define transaction conflict as a situation when two transactions try to access the same data, and at least one of them is trying to modify it. And by a transaction, we mean, an actively executing transaction here. Now, the detection of conflicts and all could be elided if you have a strictly single-threaded environment. Now, some people might ask, well, why would transactions be interesting in a single-threaded environment? Well, you still might want the all or nothing capability, the ability to wind back if you get in a situation where you sort of can't move forward easily and so forth. Now, transactions are also all or nothing. So that implies that our system needs to support some kind of rollback, undo, or depending on the exact mechanisms you use, a roll forward kind of mechanism. Now, the scope of transactions is the execution of transactional functions and transactional blocks. So as you transition from non-transactional to transactional code, that would happen at the start of a T block that is not itself in a T block or a T func, or when you call a T func from non-transactional code. And then you remain in transactional code thereafter. And there are rules that say, for example, a transactional function cannot call an ordinary function because then it would not be in transactional scope anymore. Now, this scope is both temporal, the length of time, the execution of the transaction, and spatial, it is syntactic. And this works out nicely with WebAssembly because its blocks and all are properly nested. Now, this separation, emphasizing again, transactional operations then are allowed only in the transactional scope. But non-transactional code may contain a transactional block, so you can transition into and do transactional work, and you can do that by entering a block or by a call, and then you can come back out to non-transactional code. But you can't do the opposite. It kind of doesn't make a lot of sense. Right, and non-transactional operations are allowed only in non-transactional scope. Now, there's a slight exception to this. It's safe to create or access immutable data in any scope because it's the mutation during a transaction or during execution of non-transactional code that gives rise to issues. Okay, so let's give an example. Accessing transactional linear memory. So our present scheme, every load and store opcode has a corresponding tload and tstore that would access the transactional memory. Now, this is just a comment that we could reinterpret the existing bytecodes in transactional scope if we want to. Now, the exact granularity of conflict and undo on transactional linear memory, at present we leave implementation defined. So doing it on a single byte, there's too much overhead. Doing it on a megabyte is probably too large. You want something nice and sweet in the middle. So I think roughly a cache line, maybe a little bigger. So likely a power of 2 in the linear memory. So you would take the address within the linear memory and shift it right to get the number of a granule in there to deal with. Also, each T global is a separate granule, so the T globals have conflict detected separately, individually, and the granules then are read and written. Which ones are read and written are tracked in a transactions read and write set, and they get checked on every access. Okay, so trivial example. So suppose we have a module and we want to declare and access a transactional global variable. So here's a T global, I give it the name TG, it's a mutable I32, and I initialize it to 1. Then I have a function here, it's a tfunc, and it can do a tglobal.get. And likewise, I have another tfunc that can do a tglobal.set. And these could be called from non-transactional code, and they'll run a short transaction that just accesses the one global. Now, let's look at accessing linear memory. So I have a module with a T memory with one WebAssembly page in it. And here I have a function for accessing that will do a load. And so it takes in an address and returns, in this case, float 32. And then likewise, we can do stores. So it would look something like that. Very similar to existing code, just with T's in front. Now, what about accessing transactional heap objects? So the twist we add here is transactional reference types include an access permission. Now that can be none, which says we have not established access in this transaction yet, or at least we don't know that we have. Read says we know we are allowed read access at this point. And write says we're allowed both read and write access at this point. And we add cast operators to support the gaining of the access. So tref.cast_read and tref.cast_write. And all these do is check whether you can be allowed to gain that access in this transaction. So it's where an initial conflict check might happen. And then you get back the same pointer, but with the access permission, the permissions increased so you can do more. Or you will cause the transaction to fail and unwind. Now, note that these permissions are only part of the type. They're not part of a value. They don't get stored. But this typing scheme supports optimizing the access checks needed to provide undo and conflict detection. Now, doing it this way implies that object is the unit of granularity in the heap for both conflicts and undo. Now, if this is an objection in a large array, then our suggestion is do an array of arrays, an arraylet approach. Okay, so here's an example of accessing heap objects. So we define a T-struct type that has two fields, an I32 and an F64. They should be mutable. I didn't specifically say that. And then here we have a tfunc that will create a new T-struct and return. So just the obvious code you would expect, I think. And likewise for, let's say, doing a get to get one of the fields out. Now, the key thing here that I've highlighted is you have to do a cast read on the tref coming in. So if there's no permission mentioned, it means the permission is none. Right, and then here's doing a write, similar deal. Now, here's a variation where the functions take in in this case, the constructor will return a tref that has write permission, which a newly constructed object will always have. And the getter and setter take in trefs that already have the necessary permission, so they do not have to do an additional check. So what has happened here is the check would get pushed up into a caller. So it'd be the caller's responsibility to present a pointer that has the right properties. So you can see here how this kind of hoisting of permission checks out of functions or out of loops and so forth could be an optimization. Because once you have one of these that says read or write, you can proceed to access the object in the indicated way with no further transaction checks. So this could save a lot, potentially. Now, how does all this interact with other WebAssembly extensions? Well, if you are interested in transactions but don't want GC, you can just drop the GC related types and opcodes. Threads, as I mentioned, transactions may still be useful, especially with persistence maybe, in a single threaded world. But the implementation can streamline things around conflict detection in that case. Exceptions. Now, we add a custom way of handling an exception for transaction failure, transaction abort. It doesn't rely on the WASM exceptions extension specifically, but if that extension is present, we could piggyback our exceptions on that, our single exception really. And if we further extend the exceptions extension to allow both ordinary and transactional tags, we could distinguish between exceptions that should cause transaction abort from ones that do not cause an abort, but just indicate a different sort of end of the execution. Other extensions we're aware of seem largely orthogonal to simple transactions. Okay, so review of some of the rationale. Simple flat transactions, we believe, offer the most functionality with the least burden. The segregation of types and state keeps the semantics simple. And I just enumerate some of the issues here if you do not do that segregation. The transactional reference access permissions can help reduce overheads. And we believe that leaving persistence as a separate extension is useful optionality and might improve take-up of this extension. We feel that conflicts and undo are easy to specify in terms of this notion of granules. And as I mentioned, this all seems to integrate pretty well with other extensions. Okay, so what is the status of the work? Well, I began by writing a draft specification in the style of WebAssembly extension specs from a clone of the WebAssembly GC proposal. And I have a complete working OCaml reference implementation of all of this. Tests of most of the features are available and passing. We need a few more tests in the area of conflict detection, but we've pretty much tested everything else. And then in terms of a more interesting and performant implementation, we're deeply into an implementation using Dan Titzer's Wizard engine for WebAssembly. Now, have all the opcodes implemented in his various interpreters and the simple JIT compiler, and only needs some remaining runtime support, which a lot of it is already there, so it's substantially underway and being actively worked on. We also are working on a WebAssembly to WebAssembly optimizer that could do some of that moving around of the transactional checks. So remove redundant access checks and maybe other transaction-related improvements. For example, a number of smaller short transactions might be somehow grouped together into a larger one, that kind of thing. And it would be great to have something that could actually generate code for this engine. So we have in mind adding persistence and transactions to Ben's Virgil language. Now, this is interesting because Virgil already has a WebAssembly backend. I'm actively working on extending that WebAssembly backend to support the GC objects. At present, the Virgil WebAssembly backend uses only linear memory and organizes and runs its own heap and garbage collector within that. But we wouldn't get to explore our interesting ref permissions features and so forth if we don't add support for the GC extension objects in this backend. And then the plan is to work on the language and backend extensions for transactions and persistence, which current thinking is would not be a huge compiler effort. All right, some quick thoughts on persistence before I wind up and leave some time for questions. So our notion there is to add persistent global variables. So in addition to regular global variables, transactional ones, we would have ones marked persistent, and they would be roots of persistence by reachability. So whatever objects are reachable from a persistent global, which by the way is implicitly transactional, what objects are reachable from that would become durable when a transaction commits, if they're reachable. We would add persistent transactional linear memory available. And as I mentioned, persistent things would be inherently transactional. Now, no new types are needed here in the sense of heap or value types. Now, a given WASM instance, we think it's easiest to define the extension so that it accesses only a single persistent heap. So if you have multiple WASM modules loaded, they will all access a single shared heap. But each module can present its own persistent linear memories, tables, and so forth. Now, the embedding then would support some means of connecting to a persistent store, which might likely be a file stored on some durable medium. And a store would hold one persistent heap and one or more persistent linear memories, tables, and so forth for the various modules. And there'd be a way for a module, when it's executing in the context of an already existing store, to connect up with its saved persistent things. Whoops. Okay. Right. That's it. And we have something like 5 or 6 minutes for questions.
Yeah, when I think like ACID semantics and transactions and such, I obviously start thinking about like database systems and maybe applications where the database is more integrated into the application itself. But then that makes you think of like storage formats and like B trees and other methods of laying out data for fast access and such. I was wondering if you have any like thoughts on how the storage formats for persistence and the durability aspect might work, and how whether applications would have any kind of control over like laying that data out for efficiency and high performance database systems or something. Like, could you write a database using this persistence layer? Would you have enough knobs available?
No, that's a great question. At present, trying to keep things simple, so a particular implementation would say, okay, I offer you a persistent heap, and I manage it internally. But you could certainly use all this functionality to build a database manager, say. There wouldn't be a lot of direct control over right now in what we envision over how that would be laid out in the actual non-volatile memory of whatever flavor that memory is. But that's, a great thing to think about. Would there be some kind of pragmas, annotations, whatever, that could say something about how I want this array or that struct or whatever stored.
Would it make sense to say like use transactional linear memory if you need more control over how the data is being laid out?
Yeah, yeah, that would be fine. You would have to live with whatever granularity that memory has. That is, we envision it being somewhat like the various C implementations of persistence, which tend to be oriented around uh, granules of memory in terms of virtual addresses. So I don't say 64 or 128 byte chunks that are aligned. So you wouldn't be able to do it at the database tuple level. It would be done at the byte level. But you could certainly do it. And if you know what the granularity is, you can pay some attention how you align things.